Hello again, everyone. Today I'm doing the last section of Chapter 3, which is Section 3.11. It's on something called the Tchebysheff's Theorem. It's something it's not one of my favorite topics, but it's a pretty simple one, and it shouldn't take too long, so let's just get right into it. Alright. Back in the very first chapter, we played around with the empirical rule. As a matter of fact, on the midterm, you guys had to use the empirical rule to answer some questions. That rule, when a distribution is known to be approximately normal or is bell-shaped, we can get the probability of certain intervals. That the certain amount of data, percentage of data falls within certain standard deviation units from the mean. In other words, we go out one standard deviation unit, we had 68% of the data. 2, we had 95, and out of 3, we had almost all, or 99.7%. In this section, we're going to look at Tchebysheff's theorem, and it talks about how to approximate the probability of interval regardless of the shape of the histogram. So, regardless of the shape of your distribution, whether it's skewed left, right, approximately normal, bell-shaped, U-shaped, whatever shape it might be, Tchebysheff's theorem gives us a way, like the empirical rule, it's very similar to that, in telling us how much of our data, or gives us a lower bound on the percentage of the data we expect to see within certain standard deviations from the mean. Here's the theorem for that. It says, let y be a random variable with the mean mu and finite variance sigma squared. Then for any constant k that's bigger than 0. We can't have 0 here because if you look at the formulas real quick and you plug in 0, you're going to have a problem with where the k is at in these last parts over here in the formula. Can't plug 0 in the denominator. Also, 1 would cause us an issue with one of those formulas. But this one right here gives you the upper bound, or the lower bound of the smallest probability possible when you look over a specific interval. I'm going to move this to a different slide here in a minute, a blank page, and we're going to expand this thing out to see what it's supposed to look like. And then this other one gives you a lower bound as well, but it's a little bit different. But they're actually both tell us the same information in the end. So let's look at what these things mean. Let's add a page here. So for that first one, probability that the absolute value of y minus mu is less than k times theta is supposed to be greater than or equal to 1 minus 1 over k squared. We play around with that inside bit a little bit and expand out that absolute value so it goes away. What we do is we find out this. We get y minus mu in the middle. We get less than, and on our outside tails we get a positive k times sigma and a negative k times sigma. And all of that is supposed to be greater than or equal to 1 minus 1 over k squared. The formula at the very end here is the most important part of this, but the other part helps us solve some of these problems the book likes to use. So we need to keep that in mind as well. So I'm not done yet. I kind of want to get y alone in the middle. So I just need to add mu to the outsides of the inequality so that I get mu minus k sigma, which is the mean minus the number of standard deviation units we are away from the mean. All right. Less than y, less than mu plus k sigma. That gives us an interval about the mean if we were between those two values that we come up with, mu minus k sigma, mu plus k sigma. Think about a curve, whether it's bell-shaped or not. I'll just draw a bell-shaped one anyway. But regardless of that, if you have the data value down here, mu minus k sigma, and the one up here, mu plus k sigma, and this area in here is what the Tchebysheff's inequality calculates, and that area in there happens to be the 1 minus 1 over k squared. So sometimes we just figure out what k is, and utilizing this right here will help you figure out what k is really quick, and then you can plug into that end piece to find out what your lower bound on the probability of being between two numbers really is. Okay. The other formula why I say it's equivalent is it doesn't exactly tell us the same thing, but it gives us it gets us to the same point. So in that one, just to kind of, this is also kind of a reminder for you, because we don't deal with absolute values all the time, so it's kind of nice to remember where things come from. But this thing's supposed to be greater than or equal to k times sigma, which is supposed to be less than or equal to just 1 over k squared. Well, 1 over k squared is just the complement of 1 minus 1 over k squared, so you can kind of see this is going to give us a different outcome in the end. But what is that outcome really telling us? Well, if we expand out that absolute value, we get the following. We either get that y minus mu is less than or equal to, because when you have an inequality that's greater than or equal to some value, you have to flip-flop the first one and negate that value on the right hand side, or this is one of those or situations, or you have y minus mu is greater than or equal to k. So this stays the same direction as the original formula when it's positive. Alright, so all that has to be less than or equal to 1 over k squared. And just clean up a little bit more and make it look good. It's either telling us that the y variable that we're getting is going to be less than or equal to mu minus k sigma, or y variable is greater than or equal to mu plus k times sigma, which again is the same as 1 over k squared. So pictorially what that's telling us, or what that 1 over k squared is telling us, my rough looking picture there, is that's mu minus k sigma, so this is the same setup. And you're probably guessing correctly that since it's the complement of the event that we had up top, that the area is talking about the area that's out here in the tails when we're talking about being either less than this value here or being greater than this value here. So we're talking about the area in the curve in the tails, and that area is just one over k squared. You'll use the one up top more often than you'll use the one in the bottom, but that's why they give you both of them in the book, just in case they decide to mess around with you on the inequality symbol. So the place to pay attention to that realistically is within the original formula. Definitely pay attention to, if they talk about being between two, this is the one you're going to use more often than not. Sometimes they'll do this to you too. I won't do both. I'm going to stick with this one because Tchebysheff, like I said, is not my favorite thing. I see its usefulness, and they like for us to teach this to you in statistics courses, but it's somewhat important in the realm of all things. But I can probably count the number of times on one hand I've actually used it in real life. I don't even think I can use maybe more than 2 or 3, maybe 3 times in real life that I've ever actually used it. So it doesn't come up that often. Okay, so let's do an example to kind of look at how we use this. The number of customers per day at a sales counter Y has been observed for a long period of time and found to have a mean of 20 and a standard deviation of 2. The probability distribution of Y is not known. Therefore, that's telling us that we don't know the skewness of this distribution. We don't know if it's bell-shaped or anything. What can be said about the probability that tomorrow Y will be greater than 16 but less than 24? So basically, what's the probability that we fall between 16 and 24? Okay, so we don't know K from the formula on the previous page. And they're asking us to find the probability that Y falls between 16 and 24. Alright, so we've got some work to do, but before I start building out the formula, I noticed on the previous slide what I did that might be useful to us are this formula here and this formula here. Either one of those really works. I'm going to use them both, even though you don't have to. You can use one or the other in this situation. You do not have to use both, because they both should give you the same value for k. Because the distance between the two, the k should be the same value, because you should be the same distance from the mean, and both below the mean and above the mean. So they won't both be necessary, but I'm going to do them both anyways. Down here, I'm going to do a little side work. Note that mu minus k sigma on the bottom half, the bottom one, is equal to 16. Similarly, mu plus k sigma equals 24. So we know the mean and the standard deviation was given to us. So that's saying that 20 minus sigma is 2 times k is equal to 16, and 20 plus 2 times k is equal to 24. So we just need to solve these things for k, and if they're the same thing, great. That means we know what k is. So subtracting 20 from both sides real quick, I get negative 2k equals, that should be negative 4, 5 through by negative 2k, or just negative 2, sorry, negative 2, and we get that k equals 2 here. Should get the same thing over here. If we subtract 20 from both sides, we get that 2k equals 4, and divide both sides by 2, you get the k equals 2. So there's what we wanted to know, k equals 2. Again, you don't have to do both sides of this situation, but it's nice to know that they are equivalent. They need to be. Otherwise this function or this formula won't work. So back up top here, this is saying that the probability that no matter what our mean is, mu minus, now we know k, I'm going to plug that in, 2 sigma is less than y, is less than mu plus 2 sigma, which is supposed to be equal to 1 minus 1 over k squared, which is equal to 1 minus, it's actually not supposed to be equal, it's supposed to be greater than or equal to 1 minus 1 over 2 squared, which should give us 3/4 in the end, which is approximately equal to 0.75, or is equal to 0.75. So the lower bound on the probability that the number of customers will fall between 16 and 24 is 0.75 or 75%. So this means the customers tomorrow will be between 16 and 24 with a probability of 0.75. That's kind of how you explain what's going on there. That's pretty much literally all there is to Chebyshevs. Let's do one more example just for good measure. Let's do this next one here. Let y be a random variable with a mean of 12. So we know mu is equal to 12. And a standard deviation of 6. What can be said about the probability that y is greater than 3? It's greater than 3 but less than 21. Now, I love that this book likes to reword things, but let's say we're really looking for the probability that y is greater than 3 but less than 21, so it's really not saying anything different than what we did in the last problem. And we know that's going to be 1 minus 1 over k squared, and we need to know what k is. So we're asking again, what is k here? So let's do that. So if we think about it this way, we've got, again, mu, let's just do mu minus k sigma. You can do plus if you prefer. And that's supposed to be equal to 3 on the bottom end. Well, we know that's 12 minus sigma is 6 times k is supposed to be equal to 3. So let's solve that thing again. So minus 12 from both sides. When we get negative 6k equals negative 9. Divide 3 by negative 6. And we get that k equals 3/2. You'll get the same thing, I promise you, if you do the plus. Okay, so we know what k is. So quite simply, we can say, well, the probability will be between 3, greater than 3 but less than 21 if with a probability of 1 minus 1 over 3/2 squared, which is going to give us roughly, let's see, it's going to be 1 minus, flip that around, that's 4 over 9, which equals 5/9. And that should be approximately equal to 0.5556. Double check myself since I'm on live lecture, but I'm pretty sure 5/9 is 0.5 repeating, and it is. Alright, so you can either leave it as this or this. Probability that y will be between 3 and 21 is 0.5556. You could probably just say 0.56 there. So back when we were dealing with empirical rule, one of the things we saw was k was always, like our k there, how many standard deviation units we were away, was always a solid number, like a whole number. Here in Tchebysheff's world, you don't have to have your k be a nice number. It can be a fraction. So expect that. And that's pretty much it. I guess I could do one other example. Specifically, 3.167 is very similar to what we just did here, and if you do it, you'll probably get the correct answer. But B is one of those problems where it may be a little funky. So let's do that real quick. I'll add a page in here, and we'll do from the textbook problem. Problem 3.167. We're going to do part B. A, I'll leave up to you. That's you. So in that problem, they've given us some information. The beginning of the problem says, let y be a random variable with a mean of 11 and variance of 9. Use Tchebysheff's, basically. I'm already going to butcher this name. Tchebysheff. I'm going to tell you a little bit about Tchebysheff in just a minute. Theorem defined. Part B asks us to find the value of C such that the probability that the absolute value of y minus 11 is greater than or equal to some value of C is less than or equal to 0.09. The reason I wanted to do this one is because this is the other version of that formula. That 0.09 represents the area in the tails. You could subtract from that 0.09 and assume 0.91 and probably do this problem using the other formula, but we're going to use this one. So what do we know? We know the following. We know that mu is equal to 11. I mean, it's already in the problem already for us. And we know sigma is equal to, since the variance is 9, the standard deviation is equal to 3. So you have to take the square root there. And we also know the following formula above right here. So we really know the probability that the absolute value of y minus mu from Chebyshev's is greater than or equal to k sigma, which is less than or equal to 1 over k squared. This part right here represents C. Okay. And we know that this part here is equal to 1 over k squared. So that's useful information. So if we play around with that 1 over k squared first, 1 over k squared is supposed to be equal to 0.09. If we solve that thing for k, we get that k squared equals 1 over 0.09. And take the square root of both sides of that thing, and what you'll find is that k is actually equal to square root of, this will end up being 9 over 100, so 100 over 9, which equals 10 thirds. So we know k equals 10 thirds. That's an important piece of information there. We know that c is equal to k times sigma. Since k is 10 thirds, and we know sigma is equal to 3, plugging that in back up here, then we finally get arrived at c is equal to 10. And that's all they really wanted you to find there, but I wanted to do an example excuse me, using the other formula so you could see it. Most of the questions they ask in this section in the homework in the book does not use that secondary formula. It uses the first one, but this is the one where I saw that they did this on, so I wanted to do that for you. A little bit about Tchebysheff. He's a Russian guy, and if you try to spell his name out in Google to look him up, you will find that his name is spelled like 3 different ways, at least. Matter of fact, if you just look up spelling, let's see if we can get this to come up, because I think this is kind of fun. Spelling of Tchebysheff. So it automatically said, did you mean show the results for Tchebyshev or Tchebyshev? And so there's a couple of different versions of the way they spell his name. I've always found that interesting. It's almost like it's a Russian name and they couldn't figure out how to spell it phonetically in English. So you'll get different textbooks will have his names actually spelled in different ways. The 2 you see here at the top of the page are the ones you see most often with this, just with a C, but there's a silent T. So I'm assuming that in the native language it was pronounced Tchebyshev, or with a little weird T kind of thing. But apparently with the T is the French translation of the name, versus oh, we don't want to read through all that, good lord. Oh yeah, there's one where there you go, that's where I was talking about, right there. Let me blow that up a little bit so we can see it a little clearer on the screen there. Look at the different ways this person apparently did some research of the different ways they've spelled the man's name. I've actually seen it spelled the way I spelled it, the way this book spells it. I've seen it this way here, Tchebyshev. I've seen it Tchebysheff, and I feel like I've seen a combination of those two, where it starts with a T and ends with a V too. So I just thought that was interesting. Different people spell it different ways. So, anywho, that is all for this lecture. I won't keep you on for any longer. If you need any help with the homework on any of this stuff, please let me know, guys. Talk to you later. Bye.